In section 6.6a, we are going to be working with function operations. We will be adding, subtracting, multiplying, and dividing. In 6.6b, you will learn something called compositions of functions. For now, let's just start with adding and subtracting. To add functions, what you're likely to see in function notation is something that looks like this. F plus g of x. What that means to do is to take the function that's f of x and add it to the function that's g of x. Pretty straightforward. Subtracting is very similar. To subtract functions, you will see it written f minus g of x. And what that means to do is f of x subtract g of x. Now, I do want to give you a bit of a warning on subtraction. I would suggest putting that second function inside a big set of parentheses because we need to remember that this subtraction symbol here means that we need to change all of the signs for g of x, not just the first sign. So I will be showing you some examples with that right now. I'm going to use the same two functions. F of x is going to be 4x plus 7, and g of x is going to be square root of x plus x. And we're going to do 4 different examples here with those two functions. So A, we'll do f plus g of x. B, we will do f minus g of x. And I'll get to C and D in a second because I don't know how many lines I need. So remember that f plus g of x means what I'm going to do is take my function that is f of x and add it to my function that is g of x. So I'm going to have f of x. I'm going to add g of x. So my function that is f of x is 4x plus 7. So this is going to be equal to 4x plus 7, that's f of x, plus the square root of x plus x, that is g of x. What I'm going to do from that point when I'm adding functions is I will combine like terms. So what I'm going to get here, I have 4x and x are like terms, so I'll have 4x plus 7 plus square root of x. And there are no other like terms, so that would be the answer to f plus g of x. F of x minus g of x means that I'm going to take the function that is f of x and I'm going to subtract the function that is g of x. So my f of x function is still that 4x plus 7. And then remember that caution I told you with subtraction. I'm going to put subtract, and then I'm going to put my g of x function inside parentheses. So subtract square root of x plus x. And then I'm going to remember to distribute that subtraction into my g of x. So at this point then I would have that 4x plus 7 is not going to change. But now I will have minus square root of x and minus x. And then I'm going to combine like terms again. So I will end up with 4x subtract x, which is 3x, and then plus 7 and minus square root of x. Okay. I'm going to leave a little bit of space because I'm going to come back and I'm going to talk about domain in a second. So leave yourself a tiny bit of room there. So part C, I'm going to do g plus f of x. And D, I'm going to do g minus f of x. Now for g plus f of x, that means I'm going to take the function that is g of x, and I'm going to add the function that is f of x. Now with addition, since addition is commutative, remember the commutative property says that a plus b is the same thing as b plus a. Since addition follows the commutative property, then I don't really have to rework this problem. I know that it will be the same answer as f of x plus g of x, which I just did up there. So that's going to be the same thing. Subtraction is not commutative. So what does that mean? That means that a minus b is not the same thing as b minus a. So when I work this subtraction problem, I'm going to have to actually redo my subtraction because I'm going to take g of x minus f of x. So then my g of x function was square root of x plus x. And then I'm going to be subtracting f of x. Remember to put that in its own big set of parentheses. F of x was 4x plus 7. Because I have to remember to distribute that negative. So now I have square root of x plus x. And then that negative sign distributes to the 4x, so it's minus 4x, and to the 7, so it's minus 7. Now I will combine my like terms. The square root of x doesn't have any, so it stays square root of x. X minus 4x would be minus 3x, and then minus 7. Of course, you could put that in a different order if you'd like to. I'm just going to leave mine like that for now, because I want to talk to you about domain. Domain is kind of a big topic that we will keep talking about for the rest of the year and in your next math class, whatever that may be. So domain. The domain is all of the x values that will work in a function. So domain is all x values. I should have a dash in there. All x values for which a function is defined. Here's the thing about domain. The domain is going to be all real numbers for most functions, but it's all real numbers unless there are restrictions. So let's talk about where we get domain restrictions. So domain restrictions will happen. Right now, we're only going to have to worry about 2 times that we have domain restrictions. One of the times is going to be if you have variables in a denominator. It doesn't really matter if you have variables in your numerator, it's having variables in the denominator that give us domain restrictions. The other time that we will have domain restrictions is if we have variables in the radicand when there is an even index. So we got to figure out how to identify the domain restrictions. If you have variables in the denominator, what you're going to do is set the denominator equal to 0, and then you're going to solve for what your variables equal. Solve for x equals some whatever numbers. Might be one number, might be two numbers. And then your domain is going to be all real numbers except x equals whatever that number was that you solved for up there. If you have an even index with variables in the radicand, what you're going to do is set the radicand, which is the stuff inside the radical, greater than or equal to 0. Then you will solve for x is greater than or equal to some number. Sometimes it comes out less than or equal to some number. That's okay too. Then your domain is going to be x is greater than or equal to whatever that number would be. So let's go back up and look at the domain for f of x, g of x, and then each of our problems here. So domain for f of x, remember the domain is all real numbers unless you have variables in the denominator or variables inside a radical with an even index. Since f of x doesn't have any of those things, the domain for f of x is going to be all real numbers. G of x does have a radicand with variables in it with an even index. So what we're going to do is we're going to set that radicand greater than or equal to 0, and that will be our domain. So we take the radicand, which is x, set it greater than or equal to 0. There's no solving to be done there, so that just tells me that my domain would be x is greater than or equal to 0. Now, if we look at each of these other pieces here, each of these a, b, c, d, the domain for this function, the only thing I have to worry about is this square root of x, and I already know that that gives me a domain x greater than or equal to 0. If I look at b, the only problem I have is that radicand, so again, my domain is x is greater than or equal to 0. In part c, again, I have a radicand, so the domain would be x greater than or equal to 0. And in D, I still have that radicand, so the domain would continue to be x is greater than or equal to 0. Now let's look at our next operations, which are multiply and divide. Oops, I can't spell. Okay, multiply. That's a multiply. When you're multiplying functions, that is going to look like f times g of x equals. So this is just a little multiplication dot. I guess technically you don't have to have that dot there. It could just say fg, but normally I put the dot. And what that means to do is to take f of x and multiply it by g of x. In dividing, it'll look like f over g of x. And what that means to do is to put f of x over g of x. Now, when you have a division problem, you're introducing domain restrictions, because remember, we have a restricted domain if we have variables in the denominator. So what we're going to want to do when we have a division problem is we will factor the numerator and denominator if possible. After everything's factored, we will list domain restrictions. The domain restrictions would come from setting the denominator equal to 0. That's how we find those. And then we will cancel legally. So in order to cancel legally, you have to have your function factored. And then what I would need to do would have an exact match in the top and bottom. And then that would cancel and leave a 1, because they would divide by each other and leave a 1. So let me show you what I mean by that exact match. So for example, if I have x plus 3 times x plus 2 over x plus 3 versus having x plus 3 times x plus 2 over x. So when I say you have to have an exact match, I mean it has to be exactly the same. So in this situation, the x plus 3 would cancel, but in this situation, nothing would cancel. So kind of the way that I think about it is that when I have two parentheses that are multiplied, like I can put this in a parenthesis as well, and it would be like times 1. When I have things that are multiplied, they're like Velcroed together, and so they can be unattached from each other by canceling. But when I have things that are added, those are like super glued together. So this x plus 3 over here, this x plus 3 and this x are not the same thing. This x plus 2 and this x are not the same thing. The x is super glued to the plus 2. This x is super glued to the plus 3. So I can't cancel it with the x in the denominator. So in this one, nothing would cancel. But in this one, the x plus 3 matches exactly with the x plus 3, so they cancel, which leaves me x plus 2 over 1, which would just be x plus 2. Okay, so let's look at some examples. I'm going to write my example up here because I have lots of extra space. So in my example, f of x is going to be x squared minus 9. G of x is going to be x plus 3. And then we're going to do, A, B, C, D like we did on the other one. So in A, we're going to do f times g of x. And then in B, we will do f over g of x. We also want to look at the domains each time, because that's a good habit to get into for future problems. So domain. The domain for x squared minus 9. Remember, in domain, we only have restrictions if we have variables in the denominator or variables in the radicand. So looking at x squared minus 9, I have neither of those things. So my domain would be all real numbers. Similarly for g of x, no variables in the denominator, no even index radicands. So that would also be all real numbers. To do f times g of x, then what that means is I'm doing f of x and then multiplying that by g of x. So since I have more than one term, what I'm going to want to do is put f of x, which is x squared minus 9, inside a parenthesis, and then g of x as well, times x plus 3. And then I am going to be FOILing. So I'll multiply. X squared times x would be x cubed. X squared times 3 plus 3x. Negative, excuse me, 3x squared. Negative 9 times x minus 9x. And negative 9 times 3 minus 27. I would combine like terms if possible, but there aren't any, so this ends up being my answer. And then I need to check the domain. I don't have any variables in the denominator, and I don't have any radicals, so the domain of this ending function would be all real numbers. F of x over g of x means I'm going to put the function that is f of x over the function that is g of x. So let's see. F of x is x squared minus 9. G of x is x plus 3. Now, remember our note up here on dividing. We're going to factor if possible. We'll list the domain restrictions and then cancel legally. So that's going to be my next step is I will factor. The numerator is going to factor by difference of squares. Difference of squares is really common in working with these kinds of functions. Remember, it's f squared minus l squared, and it factors to be f plus l times f minus l. So x squared minus 9 would factor to give me x plus 3 times x minus 3. And the denominator doesn't factor. It stays x plus 3. You notice that I put that in a parenthesis. That's not really necessary, but it does help me see if I can cancel anything. But before I cancel, I want to get my domain restrictions. And since I have a variable in the denominator, that is going to create a domain restriction. And the way that I identify that domain restriction is to set the denominator equal to 0. So I do x plus 3 equals 0. I solve that to get x equals negative 3. X equals negative 3 is my excluded value. So when I get to my answer, the domain is going to be all real numbers, except x equals negative 3. I have to leave that out of the domain. So the next thing after I factor and get my domain restriction is I will cancel legally, meaning that if I have a match in the numerator and denominator, I can cancel those out, leaving a 1 in their place, which is going to leave me with an answer of x minus 3, technically over 1, but we don't usually write that. So this would be my ending answer, and the domain would be all real numbers except x equals negative 3. Okay, C. In C, we're going to do g times f of x, which would mean that I'm going to take g of x and multiply it by f of x. Now, when we worked with addition and subtraction, we remembered that addition is commutative. Well, guess what? Multiplication is also commutative, meaning that a times b is the same thing as b times a. So when I need to do g of x times f of x, since I've already done f of x times g of x, I can just go straight to the answer. I don't have to work that problem out again because I already know that it is x cubed plus 3x squared minus 9x minus 27. And since I've also looked at the domain up here, I know that the domain is all real numbers. Part D. You know what we're going to do, I bet. G over f of x, which means that we're taking g of x and dividing it by f of x. Now, just like subtraction, division is not commutative, which means a over b, or a divided by b, is not the same thing as b divided by a. So we actually have to do this problem. So my g of x was x plus 3, and f of x was x squared minus 9. Remember, when we have these division problems, what we need to do is factor if possible. F of x is the one that factors. We just did it in a different problem, so we know it factors to x plus 3 times x minus 3. My g of x stays x plus 3 in the numerator. Remember what I need to do before I cancel? Remember, I need to get domain restrictions. So my domain restrictions are going to come from setting the denominator equal to 0. So I set x plus 3 times x minus 3 equal to 0. And remember, the zero product property says I would take x plus 3 equal to 0 and x minus 3 equal to 0. Solve for x. I get x equals negative 3 and x equals 3. So my domain is going to be all real numbers except x equals 3 and negative 3. Once I've got my domain restrictions, I can go ahead and cancel legally. So I have an exact match of x plus 3, so those cancel and leave a 1 in their place. So my ending answer is going to be 1 in the numerator and 1 times x minus 3, which just leaves x minus 3 in the denominator. So that's my quotient, and then the domain would be all real numbers except x equals 3 and negative 3. Okay, there's just one other thing that we need to talk about in this section, and it's something that I call stacky fractions. It's really called complex fractions, but I call them stacky fractions because they look like fractions that are stacked on top of each other. So let me show you an example of what I'm talking about. 2 minus x over 1 over x. There's 1. Or it could also have a numerator that has an extra denominator like that. 3 over x plus 2 over 5. You can have two fractions stacked on top of each other. So like I could have 3 over x plus 2 over 1 over x. But for now, we're just going to look at, only one of them having like what I will call a subfraction. So my big fraction is 2 minus x over this thing. Then 1 over x is my subfraction, is what I'm calling it. So the strategy to work with stacky fractions is that I'm going to multiply the problem by the denominator of the subfraction over the denominator of the subfraction. So in looking at this stacky fraction, here is my subfraction. It's 1 over x. Its denominator is x. So what I'm going to do is I'm going to multiply this fraction by x over x. So that is going to give me 2 minus x times x, which is 2x minus x squared. And in the denominator, I'm going to have 1 over x times x. Well, really, x is x over 1. So when I multiply that fraction, 1 times x is x times 1 is x, and guess what happens? X and x cancel, leaving 1's in their place. So now I have 2x minus x squared over 1, which is just 2x minus x squared. Now, domain gets to be a little bit tricky. When we are looking at the domain of a stacky fraction, when I get to the end, technically this answer has no domain restrictions, but at the beginning I had a denominator. So I have to worry about this having a domain restriction. So let's talk about domain restrictions. So in my big fraction, I had 1 over x in the denominator. So when I solve for 1 over x equals 0, if I multiply both sides times x, I get 1 equals 0, which means there's no solution. In other words, no restriction. However, this also has a denominator. So I also have to set this denominator equal to 0. So when I set that denominator equal to 0, that gives me x equals 0 is a restriction. So the domain for my ending function, I have to include that. So I'll have to say the domain is all real numbers except x equals 0. Let's look at this one. So I want to know what my subfraction is. This time it's the numerator. So my subfraction is 3 over x plus 2, which means my denominator is the x plus 2. So I am going to multiply times x plus 2 over x plus 2. In the numerator, I'll have 3 over x plus 2 times x plus 2 over 1. In the denominator, I have 5 times x plus 2. So hopefully you can see what's going on here is that this numerator will combine to give me 3 times x plus 2 over x plus 2 times 1, which will then cancel, leaving 1's in their place, so that my new numerator is going to just be 3. And then the denominator will be 5 times x plus 2, which if you wanted to, you can distribute and make 5x plus 10. So that's the answer to that division or that stacky fraction problem. Now let's look at domain. So in the domain restriction area, domain restriction, I have a domain restriction of my ending problem. So I'm going to set 5x plus 10 equal to 0. That came from here. And I have a domain restriction from my subfraction. So x plus 2 equals 0. So I solve for x, I get x equals negative 2. I solve for x here. I also get x equals negative 2. So the domain for this answer, or this whole problem, would be all real numbers except x equals negative 2.